Imagine you have spent your entire life studying locks. Every lock, every mechanism, every key, and then one day someone hands you a door with no lock at all, and it still won't open. That is roughly what happened to planetary scientists last year. The James Webb Space Telescope, the most powerful eye humanity has ever pointed at the sky, looked at a distant world. And what it found made physicists reach for words they normally reserve for science fiction. A planet that, by every model we have, should not look the way it looks. Not science fiction, not speculation, observed, measured, confirmed. Today, we are going to sit with this discovery, not rush it, not flatten it into a headline, and ask what it actually means. Not just for science, but for us, for consciousness, for what it means to be a mind inside a universe that keeps exceeding your imagination. Let us start with what Webb actually is, because the tool matters before the discovery can. For 3 decades, the Hubble telescope was humanity's eye on the cosmos, and it was extraordinary. But Hubble sees mostly invisible light, the same narrow slice of the electromagnetic spectrum your eyes use. Webb sees in infrared, heat, the invisible language of the universe. Think of it this way. Imagine trying to understand a symphony by only listening to the violins. Hubble gave us violins. Webb gives us the entire orchestra. Its primary mirror spans 6.5 meters, 18 gold-coated hexagonal segments, each polished to within a fraction of a wavelength of light. It orbits not the Earth, but a gravitational sweet spot called L2, 1.5 million kilometers away, shielded from the sun by a sunshield the size of a tennis court. It is, without exaggeration, the most precisely engineered object our species has ever built. And within its first year of science operations, it did something that even its architects called unexpected. It read the atmosphere of a planet 700 light-years away. Not guessed, not inferred loosely. Read, molecule by molecule. The planet is called WASP-39b. And before we get to what Webb found, we need to understand what kind of world this is, because context is everything in science. WASP-39b is what astronomers call a hot Jupiter, a gas giant, roughly the mass of Saturn, but orbiting its star at a distance of less than 1/20th the distance between Earth and our Sun. To appreciate that proximity, imagine the Sun suddenly 4 times larger in Earth's sky. Blistering, inescapable, that is the star WASP-39b calls home. Its year, 1 complete orbit, takes 4 Earth days. Surface temperature, over 900 degrees Celsius, hot enough to vaporize zinc, hot enough to turn iron into a gas. It is tidally locked. One face perpetually baked, the other perpetually frozen in stellar night. A world bisected by its own extreme. Now, here is where the story gets interesting. To understand how Webb reads a planet's atmosphere, think of a prism. White light enters, a rainbow exits, because each wavelength of light bends differently. Molecules in a planet's atmosphere do something similar. When starlight filters through the atmosphere of a transiting planet, each gas absorbs a very specific set of wavelengths, like a fingerprint. Water absorbs here, carbon dioxide absorbs there, methane here, sulfur dioxide somewhere else entirely. This technique is called transmission spectroscopy, and until Webb, it was the province of approximation. Hints, suggestions, statistical whispers. Webb changed that dramatically. When Webb pointed at WASP-39b and captured its transit, the moment the planet crossed in front of its star, it produced the most detailed atmospheric spectrum ever recorded for any world beyond our solar system. And in that spectrum, in those dips and peaks of absorbed light, it found things that no one had prepared for. Water, carbon dioxide, carbon monoxide, sodium, potassium, all expected, all confirmations of what the models predicted. And then sulfur dioxide. Sulfur dioxide had never been detected in an exoplanet atmosphere before, ever in the history of astronomy. But here is the part that made the researchers pause. The sulfur dioxide on WASP-39b is not just sitting there, inert. It is being actively produced by photochemistry, driven by the intense ultraviolet radiation from the star itself. The star is, in effect, cooking its own planet's atmosphere, running chemistry experiments on it in real time. This is significant because photochemistry was thought to be far less important in hot Jupiter atmospheres. The models said the heat would dominate. The models were wrong. Now pause on that for a moment. We built a prediction. We tested it. It failed. In daily life, failure feels like loss. In science, a failed prediction is information. It is the universe speaking back. But WASP-39b was not done being strange. The ratio of carbon to oxygen in WASP-39b's atmosphere was not what our planetary formation models predicted. And that ratio is everything. It is the chemical signature of a planet's birth story. Where it formed, what it consumed, how it migrated. Think of it like a person's accent. You can tell, without asking, roughly where they grew up. Carbon to oxygen ratio tells us, roughly, where a planet grew up in its solar system. WASP-39b's ratio says it consumed material from multiple regions of its home disk, including planetesimals, rocky bodies that formed far from where the planet orbits now. In other words, this planet migrated. It was born far out in the cold and spiraled inward to where it sits now, scorching, bloated, utterly transformed by the journey. We suspected hot Jupiters migrated. Now, for the first time, we have chemical evidence written in the atmosphere itself. That is not a small thing. That is reading the biography of a world from 700 light-years away. But we are still not at the most unsettling part. Webb also detected signs of clouds, but not just any clouds. The cloud structure on WASP-39b appears patchy, broken, irregular. And this was a significant puzzle because previous models assumed uniform cloud decks on tidally locked hot Jupiters. The patchiness matters because it changes how much starlight reaches the lower atmosphere. It changes the chemistry. It changes the temperature profile. It changes everything downstream. One wrong assumption, uniform clouds, cascades into dozens of wrong predictions. This is how science actually works. One real observation demolishes a scaffolding of assumptions. And Webb is doing this systematically to one exoplanet at a time. Now, let us zoom out because the discovery of WASP-39b's chemistry is not just about WASP-39b. It is a proof of concept, a demonstration. It tells us that Webb can do this for other worlds, smaller worlds, rockier worlds, worlds that sit in the habitable zone of their star. For the first time in human history, we possess an instrument capable of asking remotely from across the galaxy, does this world have the chemistry of life? That is an almost incomprehensible leap. A century ago, we did not know other galaxies existed. Now we are reading the molecular breath of planets orbiting other suns. But here is where I want to slow down, because most coverage of this discovery stops here, at the facts, at the chemistry. And I think that is the smaller story. The deeper story is about us, about what kind of creatures we are, that we built this machine, aimed it at the dark, and demanded answers. Every civilization that has ever existed has looked at the stars and wondered if they were alone. For almost all of human history, that question had no method. It was only a longing. We now have a method, and that shift, from longing to method, is arguably the most significant transition in the entire history of human consciousness grappling with cosmic questions. Consider what it means to be a mind, a conscious system inside a universe this vast. The observable universe contains an estimated 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. Around those stars, planets. Around many of those planets, atmospheres. And in some of those atmospheres, perhaps, chemistry. The numbers exceed the human mind's intuitive grasp. We are not built to feel 2 trillion, and yet, here we are. One species on one pale blue dot in one ordinary galaxy, and we have built a machine that can taste the air of another world. There is something philosophically vertiginous about that. Not just impressive, vertiginous, as if the ground beneath your concept of self just shifted. Because WASP-39b's strangeness is not just a scientific puzzle, it is a reminder. The universe is not obligated to be comprehensible. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. And he was right to find that astonishing. There is no reason, no logical necessity, that the laws governing matter should be legible to a primate brain that evolved for finding fruit and avoiding predators. And yet, here we are. reading the atmosphere of a world so far away that the light reaching Webb left WASP-39b when the Franks were sacking Rome. 700 years of light travel, and we can decode what that light absorbed along the way. That is not a footnote in a science journal. That is a civilizational achievement. Let us return to the science for a moment, because there is one more finding from WASP-39b that deserves more attention than it has received. Webb's data implies that the chemical abundances in WASP-39b's atmosphere are consistent with the planet having swallowed a significant quantity of solid material, planetesimals, essentially primordial rubble, during its formation. This is called heavy element enrichment, and it has a profound implication. Planets are not clean, tidy things. They are records of collisions, scars dressed up as atmospheres. In that sense, WASP-39b is not so different from Earth. Our planet's history is also written in layers, in isotope ratios, in traces of ancient violence encoded in its chemistry. We are, in a sense, reading a kindred history from across the galaxy. What Webb has done, and will continue doing, is not just catalogue bizarre planets. It is systematically dismantling our provincial assumptions about what planets can be. Every model we had for planetary atmospheres was built from a sample size of 8 planets. Our 8. An absurdly small data set on which to base universal laws. WASP-39b is data point 9, and it is already forcing rewrites. What will data points 50 or 500 or 5,000 reveal? We genuinely do not know, and that is extraordinary. We are at the very beginning of a new chapter of observational astronomy. Now, the philosophical provocation I want to leave you with, not as a neat conclusion, but as an open question. Every time we discover a planet that breaks our models, we are forced to revise not just our science, but our cosmological self-image. What we think our place in the universe is. The Copernican revolution told us we were not the center. The Darwinian revolution told us we were not specially created. The Big Bang told us even time had a beginning. Each discovery relocated us, diminished our specialness, at least in spatial and biological terms. And yet, paradoxically, each discovery was made by us. The universe does not know it is strange. WASP-39b does not know it is bizarre. It has no audience, no self-awareness. It just is. The strangeness only exists because there is a mind to register it, because there are scientists and instruments and languages and curiosity, because there is us. And that, perhaps, is the most profound thing WASP-39b tells us. Not about itself, about what it means to be a conscious being in a universe that rewards curiosity with astonishment every single time. If this kind of thinking resonates with you, the science and what it means, not just what it measures, then you are exactly who this channel is for. Subscribe, leave a comment with the question this raised for you, and we will go deeper next time. The universe is not finished surprising us.